Okay, we're going to start chapter 7. Chapter 7 is techniques of integration. So what I might do, maybe sometime this week, I'm going to put together an integral formula sheet. I'll put together what I would use if I was in your shoes for the next exam. We've essentially gone through all the formulas because we've introduced all the functions that we're going to see. So what is this chapter about? This chapter is about technique. Right? It's not necessarily more formulas. It's about strategy, approaches to integration. So 7.1, and I find that sometimes students have this in high school. Integration by parts, 7.1. Okay, so let's go back to Calc 1. And I'm going to, no, I'm not. Let's do this. What do I have here? I have a product, right? This. If I were to take the derivative of a product, I would invoke the product rule. First, derivative second, plus second, derivative first. I'm going to choose to write it this way. Okay? So, what's the big deal? Well, let's anti-differentiate each side. And what I'm going to do, I'm actually going to anti-differentiate each side, and I'm going to flip this. So I'm going to do both of those at once to save a step. So what is that? That gives me the integral of whatever this mess is, right? F g prime. First derivative second. Second derivative first. Okay, that's this, the antiderivative of the right. And if I take the antiderivative of the left, I'm just back to F and G. It's kind of boring over here. Okay, so what can I do? Well, this is an integral of a sum, so I'm going to choose to split it. F g prime F prime. Hope I don't run out of room. We're good? Okay, we're good. Okay, so what have I done so far? All I've done is rearrange my product rule from Calc 1. I'm going to rearrange it more. I'm going to do it on the next page, though, but I'm going to tell you what I'm going to do here. I'm just simply going to move this integral to the right-hand side. F, right, F, and look back at the other sheet here. FG, right, yeah. Minus integral F prime G. Okay, so big deal. Well, I just rearranged the product rule. What I'm going to do next is I'm going to just modify notation. I'm not really doing anything algebraically or calculus-wise. I'm going to change the notation to make it look cleaner. That make sense? Okay. So I'm going to let f of x, I'm going to call f u. This is kind of the standard notation for this thing. And I'm going to rename g of x as v. Okay? Well, what does that do? Think about your differentials. Right? If I were to find the differentials of these, I would say that f prime, this is sort of written backwards, but it's equal signs, they're not backwards ever, right? There is no backwards. Yeah, here's another issue. This is going to be a problem with this marker. I'm going to try to make my U's and my V's look as different as possible. Sometimes they look the same. Man. Okay. So I just did this to make this look cleaner. This looks like a mess. So I'm going to change this all out with what you see here. And what I end up with is U dV equals U V V du. This is the integration by parts formula. Okay? So the idea is, given an integral, so you're going to be faced with an integration problem. You're going to be given an integral that is going to look like that. And what this allows you to do, you could see that this integral is different. So what you hope for is that by using this formula, whatever's over here is easier or practical or possible as opposed to this. Okay, so this is one of those things that is definitely best seen by example. I'm going to put a very sort of short little recipe as I do. Let me try to do a really easy one while I write the recipe down. Let me find one that I think is easy. Yeah, this is probably about as light as it gets. So again, going back to philosophy with integration, you look at the function. Is this a simple formula application? Can I go to my formula list and knock this out? Right? That's obviously seldom going to happen, in a classroom. So I look at this, and what do we have so far? We have U substitution. That's not going to get me anywhere. Next, I have integration by parts. So when you think down the ladder. Formula, U sub, integration by parts. Okay? So, and again, I like to write these recipes with brevity. If you want a full, something more robust, you can see it in the book. But we're going to make this decision. It has some similarities to U substitution, some. We're going to define U and dV from what we have, and we have to account for everything. Okay, so I'm going to say that U is X. Okay, so I've accounted for this, and I need to account for the rest. So if I choose U to be X, and I'm going to run out of room because I'm an idiot. Sorry. I account for the rest. Okay? Now you've made these selections, so what follows are du and v. So du is 1 dx, and I'm sorry this is in the way. It looks like hell. I find that the same way I do with u substitution, and I'm going to find v by finding the antiderivative. Right? So it's like kind of the backwards process of up here. And that's going to be negative cosine. So I define these as I wish. I define these as I wish. These two follow. And then I apply the formula. I have all the pieces I need. I have u, I have v, I have v, I have du. So I apologize. This looks kind of lousy. In fact, yeah, u v right? uv minus integral v du. Integral v du. And that'll be negative cosine x dx. Negative, negative, make that a positive. Do I know the antiderivative of cosine? Of course I do. So the recipe over here, after we've done this, we use the integration by parts formula Just fill it out, right? It's mindless at that point, right? The one thing that you're in charge of is the first step, deciding what these two things are. These come from that. These fill out the formula. The question is now, can I integrate this? Right? I can't do this. So what I've done is make it into something I can work with, right? This is the original integral. I can't work with it. I use the formula. I'm down to this thing. That's cosine. It's a no-brainer, right? Perfect for me. So the last step is to integrate. So what happens is, to go back to sort of strategy, if you go through the first three steps and you're left with something that you cannot integrate, something that you might even look worse than the original, then it's possible, not definite, that you made the wrong choice up here, that this is a poor selection. So there's a similarity there with U substitution, is that you have to make this decision. What are you going to define as U and dV? Because if I had done this, if I had switched these, say I had made U as sine and then dV is the rest, this would have crashed, right? This would have been a worse of a resulting integral. So again, it's one of these things that's repetition, right? You got to practice this stuff, and then you start to kind of see, maybe what works and what doesn't. As I do some examples, I'll give you, oh, sorry, I just had a technical hiccup there. What I was saying was, as I go through some of these examples, I will give you some kind of guidelines, rules of thumb. One thing you're going to find when you do integrals is you're going to have to go through some trial and error. You might try something. Maybe you tried U as sine, right? And you see that doesn't work. So you don't just throw in the towel. That you're going to have to try something else, and that happens. That's part of this game, right? You gotta kind of try things and work through them. As you do more, you'll start to kind of get a feel for what works and what doesn't. But don't think when you sit down to an integral problem that you're supposed to necessarily see how to do it top to bottom right off the bat, right? There's even some in the book. I've done some of the harder ones in the review section where I had to sit down for 15 minutes to figure them out. Some of them are very, very tricky. Okay. So the first example is very straightforward. This one's a little bit more interesting. So this is very common, and it's very understandable that, first of all, the answer that you see a lot of times to this is 1 over x. That's the derivative. So it's this very simple looking integral. Your brain tells you, oh, there's a formula for this. Well, we haven't seen one yet, and this is not a trivial problem. One reason it's interesting is because it doesn't really look like an integration by parts formula. You think of the integration by parts. Sorry, I've made a mess of this thing. Right? If I look at this original integral, in fact, let me rewrite it. The original integral in this example, you see a product. So very loosely speaking, integration by parts is sort of the analogous to the product rule for integration. It's not quite as clean, but you saw that it was created from the product rule for differentiation. And then point being, you don't really see much of a product here. You see a single function as the integrand. However, don't forget about this guy, the dx, the differential. That's part of the integral, and I tried to emphasize that. I think it was day one. Do not ignore this, right? If you ignore this, you'll see that it'll screw up your U substitution. It'll screw that. You won't even be able to do any of these problems if you're ignoring this. So after all that, what am I? I'm going to choose u to be ln, and I'm just going to have v be dx. So that means v is x, right? 1 dx. And du then will be 1 over x dx. Okay, so I have all the pieces here. Invoke the formula, uv. I'm going to actually write it this way. Looks better. I don't want ln xx. Looks silly. Minus integral v du. So I notice when I multiply v and du, these x's will cancel out. I'm just left with dx. And that's nice because that's trivial, right? So again, the idea is you go from something you don't know how to work with to something that you do. And this integration by parts technique applies to several integrals that we haven't seen antiderivatives for, such as these. I don't even need to write them all. The arc functions. And again, you automatically think, oh, this is equal to, 1 over root 1 minus x squared. No. Okay? The arc sine, cosine, and tangent are done with this technique. ln is done that way. I guess that's it. Keep that in mind. Let me show you something else now. Uh-oh. Got to reload. Okay, this is an example that I think is a little bit more representative of what you might see on an exam. Let's go with x squared e to the x. That work? Okay, again, you see sort of this product. It is a product, not sort of. It is a product. And that might be a cue that this is the appropriate technique. So let's let u be x squared. dv is the rest. And again, you have to account for everything. I can't just pick and choose and leave stuff out, right? So easy antiderivative here. 2x dx. Okay, invoke the formula. uv minus integral v du. I'm going to choose to pull the 2 out. I like to pull constants out of integration problems, integrals, excuse me. And I'm left with x e to the x dx. Okay, so you say, well, this isn't looking much better. I don't know what to do. What are we going to do? We'll do it again. Okay? There's no reason I can't apply this technique to the resulting integral. I'll let u be x, dv then is e to the x dx, v is e to the x, du is 1 dx. So if you do it more than once, just a word of caution, sometimes you see this, it is hot in here. Don't forget about the rest of this stuff. Don't forget about the original uv. Sometimes people will, lose that. So, and also remember, I'm replacing this integral with that entire formula. So this 2, I'm going to apply to the whole uv minus v du, the new one. Now, again, these are completely separate. This is a completely new situation down here. uv minus v du, integral v du, trivial antiderivative, right? And I'm going to distribute that 2. That'll be minus minus 2. Don't forget that. Okay, so multiple uses of the technique in a problem. And I mean, obviously, in theory, I could have this as x to the 6 and go through it 6 times. I mean, it'd be ridiculous. But so this is a good illustration of decision making. Okay, think about the 2 choices. One of them is getting its derivative taken. One is getting its antiderivative taken. Let's go back to, let me write this down real quick. Just jot this down. Okay, the resulting integral has v du. So you have to integrate what comes out of that stuff. So the idea is this. When I take a derivative of a power, that power is reduced, right? Bring down -1, right? The square becomes linear, the square of 2 to 1. When I take the derivative again, x to the 1, it vanishes. So this is non-technical terminology, but you're sort of trying to break down the u part, okay, the choice of u, because the u's not in the integral, right? It's outside the integral. So you want to, it's sort of like you're trying to dissolve the u, right? E to the x doesn't dissolve. If I made u e to the x, I'd have e to the x right back again. Now you could argue, well, I had it here, which is true. But if I had e to the x over here and I had x squared here, I'd be going from a square to a cube. So I wouldn't be reducing u. You want to reduce the u. That makes sense? Because the du ends up over here. If that didn't make any sense, I understand. I gotta get some water, man. It's hot. Shit. Sorry. Okay, the next example, excuse me, is a little bit bizarre. It's sort of a dirty problem. I just want you to see this. There's a few points I want to make about this. So I just made this whole dissolve analogy. E to the x doesn't change. Sine becomes cosine. That's essentially the same thing. So right away I'm thinking to myself, this might be a little bit of a tough problem. Let's see what we can do. And I'm just going to work through it and make a point. Okay, so du is e to the x dx. And this will be negative cosine. Implement the formula, uv minus v du. I got a minus minus. V du e to the x cosine. So again, the point I'm making is this looks just like that. So it looks like it doesn't work. And if you were given this problem and quit on this at this point, most people wouldn't blame you. So let me just see what happens if I do it again. This will be sine, and this will be e to the x dx. Okay? So again, I'm going to replace this integral with the integration by parts formula with the new parts. So this will be plus uv minus v du minus v du, integral v du, e to the x sine x. Going nowhere, right? So what do I do? Well, take a look at this. Remember, these are equal signs. And if I just kind of get that out of the way, it's saying this integral equals all this stuff. I see the same integral here. What can I do? I'll bring that to the other side. So I'll have two of them over here. So I'm going to rewrite this 2 is what's remaining. And I'm going to just flip-flop these two guys. Minus, I'm sorry. And I have to sort of artificially stick the C in here. It's almost like a cheat thing. The point being is that If you are working shotgun, scatter shot, chicken scratch, everything all over the place, you wouldn't have probably seen this. But if you do work in an orderly fashion, you work organized, then you would be more likely to see this. So it's just kind of a problem. I would never put this on an exam. It's like one of those things where once you see it, it's over. Like when you find out how a magician does his magic tricks, it seems like you wasted your money. I want to do one other thing. I want to do a definite integral just to put some emphasis on the notation, because there's a lot happening here, as you can see. We're going to do, I just talked about this a little while ago, arctan. So, again, arctan x, dv is dx, v is x. This marker is dying, I think. Okay, there's all the parts. I just want you to see what this looks like. I'm going to fill out the formula uv, and I'm going to use my old friend, the box. I know some people use the straight line. That's completely fine. But I'm not going to leave this uv expression without the limits. I'm putting it on that. And I'm putting it on the new integral, of course. All right, so v du. Okay, so I have this thing. I could evaluate this right now. I don't know. I'm just going to choose to do all that at the end. It's like a obsessive compulsive thing, I guess. This resulting integral is a u sub. So this will be 2x dx. So x dx is 1/2 du. Okay, so again, I'm going to rewrite this. I could evaluate. Minus 1/2. What do I have here? du over u. And I'm going to change the limits of integration, right? If u is 0, if x is 0, u is 1. And if x is 1, u is 2. ln Yep, she's dying. 1/2 ln of u, and I'm not going back to x because this is a definite integral. It should be absolute u. They're both positive. I should do it. I should instill good habits. And now I'm ready. I have everything I need. So since I'm running out of room, I'm going to simplify this real nice. 1 goes in. 1 arctan of 1 is pi over 4. 0, pi over 4. 0 gives me a 0. What comes out over here? What a mess. 1/2 ln 2, that's not simplifying, and ln 1 is 0. So don't worry about the final. It looks nasty, but that's not the point. This is an arithmetic class. So just pay close attention to the notation for definite integrals when you're doing this stuff, when you're doing any stuff. Okay? What else do I want to say? So again, I'll do this homework and I'll talk about what I was just going to say next time we get together. Okay? See you then.